So let's talk about the chi-square test of independence and do a practice problem so we can go through that. I didn't do one for the chi-square goodness of fit just because that's a bit simpler. And I figured if you can get the chi-square test of independence, then the chi-square goodness of fit test would be even easier. All right, so let's go through a chi-square test of independence and see what we can figure out. So it's been a long held sort of belief that if you ever watched a Star Trek episode, especially the originals, that if you saw anybody wearing a red shirt, that meant they were going to die. Right? The people in red shirts tend to die a lot more often. So I actually found a guy who actually went through and did a chi-square test using this example. I thought it was pretty good. So this isn't in our practice problems. I took it off of a site online. The guy used numbers related to like the total crew. So if you look at the down here, this is like 136 is the total number of crew members that are blue shirts, total number of crew members that are gold shirts, total number of crew members that are red shirts. All right, so there's a disproportionate number of red shirts because they're coming from operations, engineering, and security. And they do seem like, all right, there's quite, across episodes and things, quite a lot more of them seem to be dying. But is that in a way disproportionate or something that makes it seem like there is a dependency between the color shirt you wear and the likelihood you're going to die in an episode of Star Trek? So we're going to perform a chi-square test of independence to determine whether there's a statistically significant association between shirt color and deaths on Star Trek. All right, so our chi-square test of independence, we still need to do the 7 steps. So let's do those. All right, so step 1. Step 1 is our null. All right, so I'll just say shirt color and death are unrelated or are independent. Okay. So this is the chi-square test of independence. It is named for the sort of null hypothesis. Step 2, H1, shirt color and death are dependent or related. Okay. Great, so far so good. Step 3, nothing's changed there. Alpha equals 0.05. Step 4, we're going to declare what kind of test we're doing. We should know what test we're doing is being told. But if you start seeing things like this where it's frequencies of things in different categories, especially if there's 2 different dimensions in which the categories are broken out into like this, then we're talking about a chi-square test of independence. Okay. Step 5. We need to find a chi-square critical value with the way the degrees of freedom work. We need to have a row -1 times column -1 degrees of freedom. And that's how we're going to figure out our degrees of freedom. So that's going to equal to our chi-square critical value with. So I have 3 rows -1, so that's 2. I have 2 columns -1 is 1 equals to 2. So our critical value with 2 degrees of freedom is something we need to look up on a table. So this time we're going to go to our our chi-square table, chi-square distribution table, and see if we can find out what the critical value is. Now, the chi-square table is pretty simple. You look up the 0.05, you find your degrees of freedom. Again, our row times column degree of freedom is just going to be 2. So our critical values is 5.991. Alpha equals 0.05. 2 degrees of freedom, 5.991. So as we saw from the table, our chi-square critical value with 2 degrees of freedom is 5.991. So the decision rule is going to be if our chi-square observed is greater than 5.991, I'm going to reject the null. All right, remember the null is that these variables are independent. So if I find a critical observed value that's larger than 5.991, I'm going to reject that. I'm going to have some evidence that there is some dependency between shirt color and death on Star Trek. For step 6, we need to find the chi-square value. All right, so for step 6 here, step 6, we need to find the chi-square. So the chi-square equation equals to the sum of observed minus expected squared over expected. Okay, observed minus expected over expected. These frequencies here are the observed frequencies. So the expected frequencies are the frequencies we'd expect under the null hypothesis when they're independent. What frequencies would we expect, so we can compare the observed frequencies we have to those that we expect. All right, so that means we need to be able to figure out how to find expected values when these variables are independent. Well, the way that works is we're going to take and find the expected values. So here, the expected values are going to equal to each of the, you're going to take the row times the column values divided by the total. Okay, and that we're going to be able to make a separate expected values table. Okay, where this is blue, this is gold, this is red, and this is alive, this is dead. Okay. So we can make this by simply multiplying. So for instance, in this first box, so in the blue / alive box, we're going to get this by taking the row total 136 times the column total, which is here 390, dividing it by the total of 430. Okay, so what do we get there? 136 times 390 divided by 430. All right, let's see. 136 times 390 equals a large number, 53,000 something, 40. Okay, divided by 430 equals 123.349. So that's going to go in here. 123.349. All right, that's my expected value for the blue alive group. So I can keep going. I can do now the gold. So I look at gold. The gold alive, I'm going to take 55 times 390 divided by 430. All right, take this row total, 55, times the column total, 390. I get 21,450. I'm going to divide that by the total, 49.884. 49.884. Okay. And then for red shirts, again, if I want to find expected value for this, I'm going to take the 239 times the 390. So 239 times 390. 239 times 390 equals 93,210 divided by 430. Okay, divided by 430 equals 216.767. 216.767. All right. So far, so good. Switch over to the dead side. So now, if I want to find the expected value for this blue shirt dead condition here, I take the row 136 times 40. 136 times 40 is 5,440 divided by 430 equals 12.651. For gold shirts here, I'm actually going to look at the 55 times 40. 55 times 40 equals 2,200 divided by 430 equals 5.116. Okay. And then the dead and red shirts, 239 times 40 equals 9,560. 9,560 divided by 430 equals 22.232. Okay, 22.232 are the expected values. So these are the values I would expect if these things were not if they're not dependent, if they're independent of one another, based on just taking the values for, you know, just all the blue shirts, all the gold shirts, all the red shirts, and all the people who are alive, all the people who are dead. And if they were to distribute them out in a way that was sort of independent of one another, these are the values that we would expect. So these are the expected frequencies. Okay. So we can now do the chi-square. All right, so chi-square here is going to equal to all the observed values. So the first one is 129 minus the expected, which is 123.349. I'm going to square that, and I'm going to divide it by 123.349 squared. Let's keep going. Next one is, let's go down first. So 46 minus 49.884. It's going to be squared. And I'm going to divide that by 49.884. Keep going down to here. 215 minus the 216. 767 over 216.767. Keep going and go down the next row. Let me just make sure draw a thing here so we know that they're separate. Go down the next column, So we're here, 7 minus 12.651. I'm going to square that, divide that by 12.651. All right, keep going here. 9 minus 5.116 squared over 5.116 plus, and keep going. The last one here, 24 minus 22.232. Square that. I'll divide that by 22.232. And that's going to give me what I want. Give me my chi-square value. Alright, so let's start subtracting and squaring and things and adding all this stuff up. Let's keep track of it. So our chi-square is going to equal to 129 minus 123.349 equals, I'm going to square that. Okay. Actually, let me take it back here. 129 minus 123, or 129 minus 123.349 equals, so this is like 5.65. So if I do this part and square it, this is 31.934. All right, 31.7. That's 129 minus 123.349 equals that. Yep, squared 31.934. Right. Okay, so 46 minus 49.884 equals, squared is, so this is 15.085. Okay. 215 minus 216.767 equals negative 1.767. Squared is 3.122. All right. 7 minus 12.651 equals 5.651 negative. If I square that, I get 31.934. 9 minus 5.116 equals 3.884. Squared is 15.085. And 24 minus 22.232 equals 1.768. Squared is 3.125. 1 second. 215 minus 216.767 equals, squared is 3.122. 24 minus 22.232 equals that. Squared is 3.125, 3.126, 26. Okay. All right. So that's all the top parts. Now we need to divide. All right. So this is, so let's take 31.934 divided by 123. 31.934 divided by 123.349 equals, all right, so now we're down here, and this first part is 0.259, 0.259 plus 15.085 divided by 49.884 equals 0.302. All right, next 3.122 divided by 216.767 equals 0.014. 014 plus 31.934 934 divided by 12.651 equals 2.524 plus there 15.085 divided by 5.116 equals 2.949. And last, 3.126 divided by 22.232 equals 0.141. Okay, 0.141. Let's add all those up. 0.259 plus 0.302 plus 0.014 plus 2.524 plus 2.949 plus 0.141 equals 6.189. So chi-square here equals 6.189. Okay, if I did all that correctly, 6.189. So for step 7, we can say since 6.189 is larger than 5.991, we're going to reject the null. Again, what was the null? The null said that t-shirt color and death were independent. So we're rejecting that. So there does seem to be some kind of dependency here. One thing that's interesting about this is if you look at the actual red shirts, so in terms of contributing amounts to to the chi-square, it doesn't seem to be like the red shirts are actually the one driving this. So if you look here, so this is, if you look at the cells of each one of these, this is a blue shirt, right? The blue shirt. This is a gold shirt. This is a red shirt, right? Here's a blue shirt. Here's a gold shirt. And here's a red shirt. So the red shirts on both of these, both in terms of those that are alive and those are dead, actually are not contributing very much to this. Where you're seeing most of it is it's actually the blue shirts and the gold shirts that seem to be dying in a way that seems disproportional. So, for instance, we're expecting 5. We're expecting 5 for this, and they actually seem to be dying more than we expect. So we expect 5, and we got 9. The blue shirts seem to be dying less than we'd expect. So 7 of them died, but we expected 12 of them to die. So both of these numbers are contributing more to the chi-square than this is. The reason why this number seems large, or that red shirts seem to stand out when they get killed in an episode of Star Trek, is because there's simply just a lot more of them. There's a lot more people working operations, engineering, and security than there are on the command and helm or in the science and medical. So there's just a lot more of them. So this helps to control for that sort of base rate. We're looking at a lot more of them just in general. So it's going to seem like you see more of them dying, but they're not dying in a way that seems disproportional to what we'd expect if those things are unrelated. It really seems like there's probably more gold shirts dying than probably should be, and there's less blue shirts dying that we would expect if these things were independent. And that's it for the chi-square test of independence.